I don't remember exactly where the internet crashed. But I was explaining, we have a low amplitude disturbance at this end, periodic disturbance, low amplitude simple harmonic motion at one end. We get a simple harmonic motion of the whole string, or every point of the string goes through simple harmonic motion, greater amplitude here than here, okay? And no amplitude here if you're holding your hand still, right? But we're putting energy into the system, okay? And the energy we put into the system builds the amplitude up to the point where the stretching and contracting of the rubber band chain causes the thing to heat up and dissipate the energy I'm putting into it. So we study a little thermodynamics here in a couple of weeks, but that's kind of what we're looking at. Okay, so the half cycle of simple harmonic motion at one end induces a much greater simple harmonic motion in most of the particles, except they're near the edge. Each half pulse, if I go this way, I send a pulse down this side. Then when I come back this way, a pulse is reflecting from the other side, and this pulse matches up with this one, okay? And every time this happens, if I'm doing this at the right frequency, so that the time required for the pulse to get down there matches up with the time of half pulse, so the time it takes to get back matches up with another half pulse, okay? If that occurs, then if I'm at the right frequency, I'll get a standing wave that looks like this. We call that the jump rope mode. So that happens. Now, as we saw last time when we studied the equation, this equation gives us exactly this phenomenon where the string is straight, then it comes out like this, and then it comes out like this, greater amplitude, and then it starts coming back, goes flat, and now goes on the other side, and so forth and so on. Okay? Mathematical representation. The A sign of KX is what your textbook calls the envelope. I actually think of the envelope, whether it's rigorously what you would call the envelope, as this picture where every one of these shapes is contained within this picture, right? So we have an A sign KX on this side and a negative A sign KX on this side, and that makes the envelope within which this wave oscillates according to the sine of omega t, which is what causes all this. And I think we saw that pretty clearly last time. I hope it's true. Okay, so now we want to talk about wavelengths in the relationship between wavelength and particle velocity and frequency and all that stuff. And I got to find my chalk here, too. Okay. Now we just saw, and it took a little while, that here's your string, and here's your chain, whatever it is. It's 4 meters long in this case. Okay. When you're in this mode, at any instant, you have a waveform between here and here that looks like this, or maybe on the other side. Maybe the amplitude's a little greater, maybe less. It keeps changing. But this is what it looks like. Now, is that a complete cycle of a sine wave? No, it's not. It's half a cycle. To complete the thing, you need the rest of the cycle here, right? Because this is what a complete cycle looks like. Okay. Now, and of course, that corresponds to kx changing by 2 pi. Got to think about that. In any case, this picture, this envelope, I'll just draw the envelope, corresponds to lambda equals 8 meters. Okay. Now, you observe, if you remember what you saw, that the next mode has a peak on this side of the string and a peak on this side of the string, and they're kind of going in opposite directions. We had a little trouble getting that because the rubber band chain was not as uniform as I'd like. Apparently, I used fatter rubber bands in one end than the other, so I really wasn't paying attention to that. And it was assorted rubber bands. Usually, it works out pretty well, but it got a little weird. But you can get if you have really a chain of consistent mass density, okay? If I was using fatter rubber bands in one end than the other, the wave was traveling more slowly on one end than it was in the other. Which means that if this was the end where you have the lesser density, the wave was traveling faster here and then it had to slow down, which means part of it reflected. Now, you'll read about that, so I'm not going to do the mathematics of it, but that's kind of what's going on. That's why the chain was a little weird. Also, you know, these should be of the same length. I didn't quite draw them that way, but you get the idea. So here's the envelope for the second harmonic. Now, the frequency is greater here, right? Okay. So let's say this thing has frequency F naught. Okay. We call that the fundamental. Fundamental frequency, but we apply the word fundamental here, okay? Here, this requires a greater frequency. You know, as you sped up, first of all, this whole picture destroyed and you didn't really have, you just had incoherent oscillations going here and there along the string until you sped up to the point where you got this one, okay? So this will be frequency F1. We call this the first, actually it's the first overtone. It's the second harmonic. This is the first. Okay. Now, what's the wavelength here? Still 4 meters from here to here. What's the wavelength? Well, right there is a typical shape, right? I've drawn the whole envelope here. But this is a complete cycle, right? Well, it's now 4 meters, right? Now we can say even more. I'll put a little note up here. That's 2L for L is your length, right? So this picture applies to any string of any length. Your fundamental wavelength, and I'll call that lambda 0, is twice the wavelength, or twice the length of the string, right? Because this is what it looks like, whatever the length is. Here, now your next harmonic, what's your next harmonic look like? We're going to stop the video for a second, stop the recording, and ask you to sketch the next one. Okay, so that was quick. Everybody saw the pattern. Then what we have to do is to get the next harmonic, we can split this into 3 half cycles. And the envelope is going to look like this. So what's your wavelength? Well, you can sketch a full wave here. And what you see is that, well, lambda 2 is going to be 2/3 of your 4 meters, 8/3 of a meter. Okay. And then you could get your next harmonic. Envelope is going to look like this. And you see that here's a cycle. Lambda 3 is half of 4 meters. Okay. Now, lambda naught equals twice the length. I'm sorry, I write this down ignorantly because I'm debating about how I want to write it, which is probably not the way to get it done efficiently. Let's try again. Okay, here's how I want to write it. Okay, we see this. Well, I want to write this a little differently. I want to write it clearly so we can see exactly how to figure out the 20th wavelength. Okay, with the equation that we solved to do the 20th wavelength. So I'm going to say, well, here we have 1/2 lambda 1 equals L, 2/2 lambda 1 equals L, because we have 2 half wavelengths in here, right? And then we have 3/2 lambda 1 equals L because we have 1, 2, 3 half wavelengths. We're always going to have an even number of half wavelengths. Then we have 4/2. That should be lambda 2 and lambda 3. Lambda 4 equals L, and I got the wrong subscripts here. According to the notation I'm using, these should be lambda 0, 1, 2, 3. And these should be lambda 0, 1, 2, 3. Wipe these out without wiping out anything else. Okay. So this should have been lambda 0, lambda 1, lambda 2, lambda 3. If your book uses different notation, it's okay because you understand where it's coming from. Okay. And what you have then is n plus 1 over 2 times lambda n equals L. If you think about that, I'm not going to explain it. You should understand that if you did sequences and stuff in calculus. If not, you should review it. Okay. Well, now another thing. How about these frequencies? Because what you really want to know is not what the wavelength is. It's how fast you got to wiggle to make this thing happen. How frequently you have to, what the frequency of your simple harmonic motion it just has to be. Okay, well, your frequency is how many wavelengths there, how long it takes you to, sorry, how many wavelengths you get per unit of time, right? So, number of wavelengths per unit of time. I claim that the frequency times the wavelength equals your speed of propagation. This says your frequency is the number of wavelengths per time. I'll say times the length of the wavelength, just because maybe it's less confusing. Okay? Just the number of wavelengths you got per unit of time times the length of one wavelength, the distance of one wavelength. Let's say distance. That's distance over time, which is how fast you're moving. You need to ponder that a little bit, but it's obvious. If I have 10 wavelengths per unit of time, frequency of 10 cycles per second, okay? 10 wavelengths per unit of time, and the wavelength is this much. Well, let's say the wavelength is this much, okay? Here's your wavelength. 10 of these per unit of time means I go that far in a unit of time, 10 times this far, right? So you multiply how many wavelengths you get per second, usually, by how far you go, how far one wavelength is, and you get how far the wave has to go in a second. So you just got to think through that, but it's really a very simple fundamental picture once you get it. So it looks like a formula you ought to memorize. No, it's something you ought to understand. Or if you want to memorize a formula, fine, but make sure you understand it. Make sure you understand that this is what it's saying. One way or another, understand why the frequency times the wavelength is equal to your propagation speed. Really fundamental. It's usually what I start off with, trying to follow website. Okay. If you know the frequency and the wavelength, you know omega and K, right? So the frequency implies omega. Lambda implies K. And you got to understand the relationship between frequency and omega and lambda and K. That's more than a formula that you memorize. Because as I said last time, the formulas with the 2 pi's in different places and the lambdas and f's, sometimes in a numerator, sometimes in a denominator. No sane person without photographic memory ever tries to keep those formulas straight. You shouldn't have to rely on a formula sheet to understand these things because these relationships are very simple. Okay? So as I told you last time, you got to understand how this is related and this is related, and then how these things are related to the equation, the sine of omega t and the sine of kx and the sine of kx minus omega t, and how that gives you standing waves and traveling waves. So you want to understand all that at a very basic level. Okay, well, I need more board space, so I'm going to pause for a second. Okay, I finally got this written down, right. Okay, we saw earlier that this is this, right? This is from a simple picture. Okay, this is from simple reasoning. And this is a simple algebraic rearrangement, but it's a little more than that. Okay. Well, then lambda is this, right? So it's 2 over n plus 1 times c over L. What's c over L? Sorry. 2c over L. Figure F naught. Then you're going to have to ponder that a little bit. It's going to come up again and again, so you do want to ponder it. Simple algebra. Okay, now we're not going to take time to copy all this down meticulously. It will be posted. All this can be summarized by a simple picture that doesn't involve sine waves. Once you understand all this, okay, well, one more simple picture of sine waves. These points where nothing is moving in an ideal wave, you know, with the rubber band, you get a little wiggle everywhere. It's not all totally uniform, at least the way we're doing it. These points where you have zero displacement, ideally, are your nodes. Okay, and that includes this end and this end, because in an ideal wave, you need very small simple harmonic motion at this end to produce the wave. Okay, very small. So this end is also a node. So here we have 6 nodes. Okay. And these points where we have maximum deflection are the antinodes. Make sense? So we have one less antinode than we have nodes. Okay. Number of antinodes is your number of half wavelengths, because every antinode corresponds with half a wavelength, right? Hopefully we see these as half wavelengths. Okay. So here's a wavelength. Half that wavelength corresponds to the distance you have to suck out of the whole length of the chain in order to produce that antinode, right? That wasn't a very good statement. I think you get the idea. Here's another wavelength, right? Every one of these such that distance between two nodes is the wavelength, okay? So the distance between consecutive nodes is 1/2 your wavelength whatever the wavelength is, and the frequency follows from that. Okay. Well, this is fundamental. Okay, so if you've got any standing wave, you can detect its node antinode configuration very easily. Okay, you have a node at each end, and between any two nodes, you have to have an antinode, because that's obvious, right? Between a node and a node, there's an antinode. So right here is your fundamental configuration, right? This would be your lambda node, your fundamental. The next possible configuration, a node here, and a node in between. And of course, then you have an antinode here and an antinode here. So here you got non, here you got non. Pretty soon you got na. Okay. I'll stop singing. I don't want to put that on you. Now you're going to have two nodes in between here, and they got to be equally spaced. It's drawn that way, but okay. So this NAN thing, this na, tells you what you need to know about the wavelength. Okay. Now another thing is, from a node to a node. Okay, let's say we got this. Okay. From a node to a node, half a wavelength, right? From a node to an antinode is 1/4 of a wavelength. Well, I'm going to leave that where it is, but I want to show you something now, which is really cool. I don't know if I've showed you this before or not. Practical application. Have I done this? Are you going to want it? Okay, hold this right in the middle. Okay, balance and point right in the middle, right? That's going to produce a node here. Now I take something metallic, something heavier than this. Hopefully that this will do. Okay, what you have there is this end is doing this, and this end is doing this. Okay, opposite. If this is down, this is up. So you have an antinode here, because this end is free. You have an antinode here. That end is free. Okay? You have a node in the middle. Well, the wavelength is, well, the node to antinode distance is what? A quarter of a wavelength, right? That's about 3/4 of a meter. So that the wavelength is about 3 meters. So what you were hearing was vibrations in the air that correspond to a disturbance in this aluminum, okay, like 3 meters. Well, get more into that in lab because we're almost out of time. I guess we just ran out of time, but here we go. Here's another one. Now, I'm going to do this. Okay. Keeps going a while, doesn't it? Okay. These vibrations, the middle has to hold still because I'm holding it. If it was moving, then the vibrations would lose their energy by moving my hand or wiggling the flesh between the bone and the metal. Okay. So what's happening is the ends are doing this. Okay. So now your wave velocity in that case is the velocity through the metal. Okay. The velocity of a compression wave that moves from one end to the other and back. When I hit it on the floor, all kinds of oscillations occurred. Okay. All kinds of frequencies were there. But the ones that didn't match the end, so the reflected pulses would reinforce the incoming pulses, killed themselves. Okay, they just canceled themselves out. They didn't match up, so they interfered with each other and they went away almost instantly. Okay, the ones that were left, well, you heard the fundamental. Okay, and there were higher frequencies in there as well. You couldn't see them, you couldn't hear them because the fundamental was much louder. The combination of frequencies actually gave you the tone of what you were hearing. We'll talk about that. As I said, we're out of time. But if you look at the node antinode, now the frequency of what you were hearing there was probably around 2,000 hertz. Knowing the wavelength, we can figure out how fast the disturbance is traveling in the aluminum. If the wavelength of that was 3 meters, that means that the disturbance is traveling through the aluminum 6,000 meters per second. Okay, I don't think it's quite that high. I think it's probably around 1,500. That's probably around 4,000. You can figure that out with a simple equation, a simple formula, just like the square root of 2 over mu. You just use a different thing instead of T. And mu is still your mass per unit volume in this case. So all that stuff ties together in a way that's pretty neat. Also, if we support this thing, here and here maybe. Then we could have antinode, node, antinode, node, antinode, node. And we could reinforce that and you'd hear a higher frequency. We'll do that way. Put a couple of dominoes under this thing, tap the end with a hammer. Okay, so pretty neat stuff. Of course, you're going to have to represent it mathematically.